Something happened on a mountaintop in Chile, and most of the world has no idea what it means. Scientists stared at the data for hours. Some of them went quiet. Not because they found nothing, because they found too much. A machine built over 2 decades, costing over $800 million, pointed its eye at the sky, and in a single night it saw more of the universe than every telescope ever built in all of human history combined. And what it found in those first images did not comfort astronomers. It made them realize we have been reading the wrong map all along. There is a mountain in northern Chile rising 8,800 feet above sea level, where the air is so dry and the sky is so dark that on a clear night you can see the arms of our own galaxy draped across the heavens like a river of ancient light. This is Cerro Pachon, and always perched on its summit in an 18-story facility that houses one of the most powerful instruments ever constructed by human hands. The Vera C. Rubin Observatory has just done something that no machine on Earth has ever done before. It opened its eyes, and what it saw is already beginning to unravel what we thought we knew. The observatory is built around the 8.4-meter Simone Survey Telescope, equipped with the largest digital camera ever constructed, a 3,200 megapixel instrument so vast and so precise that a single image it captures covers an area of the sky more than 40 times the size of the full moon. Think about that number for a moment. Not a small patch of darkness, not a targeted zone, 40 full moons, in one shot, in one single exposure. And here's where it starts to feel less like an achievement and more like a reckoning. Each full image snapped by the observatory's 3,200 megapixel camera would require 400 4K high-definition television screens to display at its original size. You would need to fill an entire basketball court with the highest resolution televisions money can buy just to look at one photograph. And this machine is designed to take roughly 1,000 of these images every single night, sweeping the entire southern sky completely once every 3 to 4 days, and then starting again over and over and over for 10 consecutive years without stopping. This is not a telescope. This is a time machine pointed at the future of everything we think we know about reality. But here's where it gets more unsettling. The images that have already come back, in just the first test observations alone, did not simply show us beautiful nebulae and familiar constellations. They showed us things we were not expecting to find. And the scientists who dedicated decades of their lives to building this instrument, the people who know more about the cosmos than almost anyone alive, looked at the early data and used words like humbling and transformative. That is not the language of comfortable confirmation. That is the language of people recalibrating their assumptions in real time. In just over 10 hours of test observations, the Rubin Observatory had already captured millions of galaxies and Milky Way stars and thousands of asteroids. Let that land. Not years of operation. Not months of systematic observation. 10 hours. 10 hours of pointing this camera at the sky, and it returned data containing millions of objects. Many of them objects that no human being had ever seen before that moment. The scale of what this telescope is doing to our understanding of the universe is difficult to put into language, because the language we have was built for a universe we thought we understood, and that universe is getting smaller by the hour. One of the first images released shows the Virgo cluster, a vast collection of galaxies located around 53.8 million light-years from Earth. That single image alone contains approximately 10 million galaxies. And those 10 million galaxies represent just 0.05% of the roughly 20 billion galaxies that Rubin will have imaged by the end of its 10-year survey. Read that again, 10 million galaxies in one photograph. And that is less than 0.1% of the final total. By the time the survey ends, Rubin will have collected data on an estimated 40 billion individual celestial bodies. Which means, for the first time in human history, we will have directly observed more objects in the cosmos than there are human beings alive on Earth. We have been calling ourselves a civilization that understands the universe. That title is now under review. And this is where everything changes. Because the beauty of the images is not what has the scientific world paying urgent, quiet attention. What has them leaning forward, whispering in corridors, is the question that this machine was specifically built to answer. A question that has been hanging over physics and cosmology for decades, like a locked room at the end of a long hallway. The question is this: what is the universe actually made of? Because the answer, according to everything we currently understand, is that we have no idea what 95% of it is. It is a basic fact in modern astrophysics that the familiar objects around us, people, planets, stars, account for only about 5% of what exists. The rest is dark matter, which helps hold the universe together, and dark energy, which is thought to be responsible for the universe's accelerating expansion. But what these invisible phenomena are made of is barely understood. 5%. Everything you have ever touched, everything that has ever been seen or felt or measured, every atom on Earth, every star and every galaxy and every image ever captured by every telescope ever built, all of that represents 5% of what the universe contains. The other 95% is invisible. It does not emit light, it does not reflect light, it does not interact with light in any way that our instruments have previously been able to detect. And yet, it is the dominant force shaping the structure and fate of the entire cosmos. This is not a minor scientific footnote. This is the central unresolved crisis of modern science. The woman this observatory is named for understood this better than almost anyone. Vera Rubin was an American astronomer who, in the 1970s, found evidence so uncomfortable that the scientific establishment initially refused to take it seriously. Working with her colleague Kent Ford, she discovered that stars at the edges of galaxies were not moving slower with increasing distance from the center, a phenomenon that could not be explained on the basis of visible matter alone. This led to the revolutionary conclusion that a large portion of the universe is made up of dark matter, an invisible substance that, as far as we know, exerts gravitational force without interacting with light. She was right. The establishment was wrong, and she spent the rest of her life being recognized as one of the most important scientific minds of the 20th century, without ever receiving the Nobel Prize that her discovery almost certainly deserved. The telescope bearing her name was built to finish what she started. But what is coming? Back from that mountaintop in Chile is suggesting that the story is far more complicated than even Vera Rubin imagined. Dark matter makes up about 80% of all matter in the universe, and its properties affect how galaxies form and grow, as well as how they clump together to form long filaments that make up what scientists call the cosmic web. But shaping the large-scale structure of the universe is a game of cosmic tug-of-war between dark matter and an elusive force known as dark energy. Dark matter tries to build cosmic structures, while dark energy acts to dilute them and push them apart. Two invisible forces, neither of them understood, one pulling things together across the void of space, the other driving them apart with accelerating force. And in between, the thin, visible layer of matter that we call the universe, stars, galaxies, planets, people, stretched between these two forces like a web of light over an ocean of darkness. The Rubin Observatory's primary mission is to map this darkness. And the early results, even from preliminary observations before the full 10-year survey officially launched on June 30th, 2026, are already generating urgent scientific conversations. Researchers examining the first images have already made numerous new discoveries. Among the most striking, young galaxies harboring supermassive black holes far larger than they should have had time to grow. The young galaxies should not have had enough time to develop black holes even 1,000 times more massive than the one in our own Milky Way. It is, in the words of one researcher, like discovering a full-grown adult in a kindergarten class. This is not a minor anomaly. This is a structural problem with the way we understand how the universe evolves over time. Either these black holes grew in ways our models do not account for, or something else is happening in the early universe that we have not yet theorized. Both possibilities are deeply uncomfortable. But think about what that means for the 10 years ahead. If the first handful of test images have already produced findings that challenge our models of galactic evolution, what happens when the full survey is running, taking 1,000 images per night, sweeping the entire sky every few days, generating 20 terabytes of new data every single evening? Each night, Rubin Observatory is expected to collect approximately 10 terabytes of data and eventually generate as many as 7 million. Alerts identifying objects that have moved, appeared, disappeared, or changed in brightness. Those alerts will flow into automated systems known as alert brokers, which classify the changes and help astronomers decide which events deserve immediate follow-up observations. 7 million alerts every night, not per year, per night. The universe is doing something different every few hours, and for the first time in history, we have a machine capable of catching it in the act. There's a particular discovery that has not received nearly the attention it deserves. Through images taken to help optimize the new system, the observatory has already detected 11,000 new asteroids and logged dozens of other new objects in the solar system. 11,000 asteroids before the full survey even began, before the machine was properly calibrated, before the algorithms were fully optimized, before a single official night of science operations had been logged. And the reason that number matters is not merely academic. Some of those objects have orbital paths that intersect with the inner solar system. Some of them have trajectories that bring them closer to Earth than any previously cataloged object. The Rubin Observatory was specifically designed to serve as humanity's early warning system for near-Earth threats, and it has already, in its opening weeks of operation, dramatically expanded the known inventory of potentially significant objects in our cosmic neighborhood. This is not chaos. This is discovery at scale, and it is accelerating. Rubin will be able to identify subtle irregularities in stellar streams, trails of stars left behind when smaller galaxies fall into the Milky Way, caused by dark matter clumps passing through them. These interactions appear as kinks and gaps in the starry trails, and by analyzing them with Rubin's detail, scientists hope to narrow down not just the distribution of dark matter across the galaxy, but potentially the specific type of particles it is made of. The implications of that sentence are almost impossible to overstate. We are not talking about confirming that dark matter exists. We already know that. We are talking about using the gravitational fingerprints left in stellar debris to deduce the particle physics of an invisible substance that makes up the majority of all matter in the observable universe. If that works, and according to informed sources within the collaboration, the early data suggests it might, it would represent the single most important advance in fundamental physics in over a century. The scale of data being generated by this observatory is unlike anything the scientific community has previously had to manage. During its 10-year survey, Rubin will generate approximately 20 terabytes of data per night, plus an additional 15 petabyte catalog database. In 10 years, Rubin data processing will generate around 500 petabytes, and the final dataset will contain billions of objects with trillions of measurements. 500 petabytes. To put that number into context, a single petabyte of data would take approximately 300 years to listen to if converted into audio. Rubin will generate 500 of those, and all of it will need to be processed, filtered, analyzed, cross-referenced, and interpreted by systems powerful enough to handle a data stream that no single human mind or institution could manage alone. This is why the observatory has built one of the most sophisticated automated data processing systems in the history of astronomy. Machine learning algorithms trained on hundreds of millions of existing astronomical observations will scan every new image in real time, comparing it against previous captures of the same patch of sky, flagging anything that has changed, anything that has moved, anything that has appeared or disappeared, and dispatching those millions of nightly alerts to research teams around the world within 60 seconds of detection. The universe changes constantly. For the first time, we will be watching it change in real time, globally, with institutional precision. What most people are not fully grasping about this moment is not just what Rubin has already found. It is what Rubin is designed to find that nobody has thought to look for yet. The images will reveal asteroids and comets, pulsating stars, supernova explosions, far-off galaxies, and perhaps cosmic phenomena that no one has seen before. That last phrase, phenomena no one has seen before, is not marketing language. It is a scientific prediction grounded in statistical certainty. When you survey 40 billion objects over 800 separate observations each, the probability of encountering something entirely outside existing theoretical frameworks is not small. It is near certain, and whatever those unknown phenomena turn out to be, they will arrive in the data stream without warning, flagged by an algorithm that can identify them as anomalous but cannot tell us what they mean. That interpretation will fall to human scientists. Scientists who, by that point, will already be overwhelmed by 7 million other alerts from the previous night. Rubin Observatory. Chief Scientist Tony Tyson has described this moment as a turning point, not just in collecting more mysteries, but in actually beginning to solve them. It is a turning point because we're going to be able to do something totally new with very high precision, he said. Very high precision is the key phrase, because the problem with dark matter and dark energy has never been that we lacked evidence for their existence. The evidence has been there for decades. The problem is that we lacked precision. Our instruments could detect the gravitational influence of dark matter on galaxy rotation, but they could not map its distribution with enough granularity to tell us what it actually is. Rubin changes that, and the first maps are already beginning to emerge. There's also a dimension to this story that almost nobody is discussing openly, but which informed sources close to the collaboration are watching carefully. The Rubin Observatory will, over its 10-year survey, build up a time-lapse record of the entire southern sky at a level of precision that has never before existed. This means that any object in the southern sky that behaves in an unusual way, that changes brightness unexpectedly, that moves in a pattern inconsistent with known orbital mechanics, that appears and then vanishes without spectroscopic explanation, will be flagged automatically within 60 seconds and sent to researchers around the world for immediate follow-up. The implications of a system that watches everything in the sky with this level of vigilance, this level of consistency, this level of speed extend well beyond standard astrophysics. We will know, for the first time, if anything up there is doing something we cannot explain. As one board member of the LSST Discovery Alliance put it, if something in the sky moves or changes, Rubin will detect it and distribute the information in real time to the entire world. This means that we will be able to observe transient phenomena in action, making new, often unexpected, astrophysical discoveries possible. Every night, without exception, for 10 years. A planetary surveillance system pointed not inward at human behavior, but outward at the cosmos itself, watching for the unexpected with mechanical patience and algorithmic precision that no human observer could maintain. The story of the Vera Rubin Observatory is also, in a quieter way, the story of what science has to do to survive the scale of its own ambitions. The observatory is a collaboration involving researchers from dozens of countries, with the LSST Dark Energy Science Collaboration alone numbering over 1,300 scientists, across more beings, across generations, across borders, across decades of setbacks and funding fights and technical failures and rebuilt systems. The first engineering image from the camera came in October 2024. The first light images were released on June 23, 2025. And full survey operations officially began on June 30th, 2026, more than 2 decades after the project was first formally recommended as a scientific priority. 2 decades. Think about what was happening in the world in 2001. The internet was still finding its shape. Smartphones did not exist. The human genome had just been sequenced for the first time. And somewhere in a conference room, a group of astronomers were drawing up the specifications for a machine that would not open its eyes for another 25 years, designed to answer questions about a universe they could barely measure. That kind of long horizon thinking, that willingness to build something for future generations rather than for immediate results, is rarer than any cosmological phenomenon Rubin will ever photograph. And it is the only reason the images now coming from that Chilean mountaintop exist. But here is what no one is saying out loud quite yet. The data is only 7 days old in its full operational form. The real survey began June 30th, 2026. The algorithms are running. The alerts are being dispatched. The collaborations are comparing notes. And already in the first week of full operations, there are objects in the data stream that do not match expected behaviors. Objects whose light curves are inconsistent with known variable star classifications. Objects whose positions shift in ways that suggest they are closer than anything in our asteroid catalogs. Objects that appear in one night's image and are absent in the following night's capture of the same region. Most of these will have mundane explanations. Most of them will be instrument artifacts or atmospheric interference or objects previously known and imperfectly catalogued. But not all of them. Statistically, not all of them. As distinguished Professor Saurabh Ajah put it in describing Rubin's mission, the universe is always changing. Stars explode, black holes flare, and objects move across the sky, often on timescales that make them easy to miss. Easy to miss. Until now. Because the thing that changes with Rubin is not just sensitivity or resolution, it is continuity. Previous observatories would watch a patch of sky for a night, then move on. A phenomenon that lasted 3 days would be missed if the telescope was pointed elsewhere. Rubin watches everything, repeatedly, relentlessly, without interruption. It does not blink. And in a universe full of things that only show themselves briefly and unexpectedly, not blinking is everything. The final number that should settle in your mind before you go on with your day is this one. By the end of the 10-year legacy survey of space and time, Rubin will have collected data on an estimated 40 billion celestial bodies, more than the number of human beings who have ever lived on Earth. And every single one of those 40 billion objects will be cataloged, measured, revisited, and analyzed. Every one of them will have a light curve showing how its brightness changed across 800 separate observations. Every one of them will be cross-referenced against the 7 million nightly alerts generated by everything else in the sky doing something unusual that same night. This is the universe at scale, not the universe as we imagined it, not the universe as we wished it were. The actual universe, mapped with a precision that no generation before ours ever possessed, and most generations after ours will take for granted without understanding what it cost to build. And the most important thing about what Rubin is finding is not any single discovery. It is the suggestion, growing stronger with every night of new data, that the universe we thought we understood, the 5% we could see, the models we built to explain it, the theories we taught in every university on Earth, was always, from the very beginning, just the surface. Below the surface, invisible and massive and old beyond comprehension, the rest of it waits, dark, patient, real. And as of this week, for the first time in history, we finally have an instrument powerful enough to look directly at it and refuse to look away. The question is whether we are ready for what it is about to show us.